Uh, Good morning to all of you again. Uh, well, my topic, my talk now is quite in contrast with the earlier talk we had in many ways. I'll talk about the finite simple groups, which are much fewer in number than the P groups. It's not nowhere near 99% or something. And the second thing is that I would have hardly any proofs. I mean, this is more some kind of a snapshot. In fact, a snapshot from a satellite, if you like, about this huge and immensely important this program of the classification of simple groups that has happened. And the classification of simple groups, I mean, this finite simple groups, all of you know, just has been classified, or at least most people in the business think that it is classified. And this has been like this a great achievement of like this 20th century mathematics. And I'll just give a rather very brief just overview of some of the high points of this endeavor, and also just mention some of this. Well, it has lots of this very great ideas. In fact, this is a huge enterprise, as all of you know, and I'll just concentrate on just a couple of ideas, which perhaps which will have some bearing to the monster and its construction and so on. So this is roughly just the topics which I would like to just talk about. Introduction. There are two families of this simple groups, groups of Lie type and sporadic groups. And this main theme in this classification has been the importance of involutions that has been just recognized, and I'll just spend some time on that. And there's another very major theme, the group generated by transpositions, which is a very natural way some of the geometric ideas enter into this group theory. And very briefly about our protagonist monster. Monster is rather quite monstrous, and there will be a couple of other series of lectures on the monster and its connections to modular forms such moonshine and modular forms and so on. So I'll just briefly indicate some connections to this monster. And very quickly, classification of finite simple groups is a very major achievement involving hundreds of people and hundreds of journal articles, about 400, 500 journal articles. And it's a huge project. And my objective here is only to just indicate, just some of the high points of this endeavor. And there are two aspects to this. One is discovery of new simple groups, and then just showing that your list is complete. List of whatever you just do is complete. And of course, simple groups always mean finite non-abelian simple groups, because abelian things all of us. Very quickly, some history before that. You see, until 1950s, the activity in group theory was rather minimal, and I think even in the early 1910s, 20s, and so on, people were saying that group theory is essentially a dead subject. But there were some very major breakthroughs. Jordan-Holder theorem. Well, first of course, normal subgroups and simple groups were defined by Galois, and in his this famous thing relating the solubility of groups and its relations to this solving equations for radicals. Jordan-Holder theorem says its main importance in the structure of groups, and Jordan listed a few matrix groups in the first book on Galois group theory. And of course, this Matthews construction of this highly transitive groups, this was in 1860, 61. But of course, one of the most structurally important results is like the Solo's foundational theorems, the Solo theorems that every undergraduate has to learn. And in the early part of this 20th century, Dixon realized a few groups as in analogy with matrix groups, as the stabilizers of certain multilinear forms of these vector spaces, like E6, for example, is one of the groups which exists. And of course, the monograph of Dieudonné, and importantly, representation theory developed by Frobenius, Schur, and very famous and very important work of Philip Hall on the solvable groups, and Brouwer's initial starting of the representation theory over fields of characteristic T, the non-Masch case. And Grun's work on transfer, though it is perhaps not very popular, but this is a very important thing, and the Hall-Hickman theory. These were essentially the main things. Hall-Hickman theory perhaps is also 1950s, but these were just the high points of the Galois of the group theory in the first half, up to the first half of the first 20th century. But in 1950s, there were three very major breakthroughs that happened. One was Richard Brouwer's announcement that simple groups, he was only talking about simple groups of even order. He just announced that simple groups of even order could be classified by centralizers of their involutions. That is, you just take the centralizer of an involution of a known simple group, you take the structure of the centralizer of the simple structure of the centralizer of a simple group of that you know, and try to classify all simple groups which has involutions, centralizers of that set. And of course, this the major work of Claude Chevalley. In fact, in 1950s, in his young days, he boasted to Andhra Vail that he would algebraize Lie groups to death. And that is essentially what he did in his the Tohoku paper. He gave a very general construction of the analogues of Lie groups for arbitrary fields. This is a very major theme. This not only put all these the classical groups, the matrix groups in a uniform platform, it also constructed a new, then unknown simple groups. But the most important thing is that it gives essentially a platform to understand these classical groups and other groups in a uniform way. We'll talk a little bit about that. And one major common feature of these groups which Chevalley constructed is that they admit a very distinguished double coset decomposition. This double coset decomposition essentially is, in the case of GLN, for example, what we see as the row reduced echelon form. That's essentially what it is. That is, any matrix, any element of GLN can be written as a upper triangular matrix, a permutation matrix, and another upper triangular matrix. That's what this Bruha decomposition comes to. And this was and you see, this in this Bruha decomposition, the components are indexed by a symmetric, by a finite permutation group, and it doesn't matter on what field you just take these groups. So this is a very remarkable kind of achievement. The finiteness of the set from which you can index these double cosets. And this was the basis for the buildings, spherical buildings constructed by Tits, which have the property that their automorphisms essentially gives you all these groups. That is, nonabelian sections of automorphisms of this building that he constructed gives you all these classifications. And the third major breakthrough is this John Thomson's thesis, where he proved this Frobenius conjecture. just and this was the beginning of the so-called local analysis in access group theory. That is, you just try to understand the structure of the group by the normalizers of its just non-trivial P subgroups. See, the work of Grun and actually the work of other people unto that time to show the non-simplicity of a group was to create criteria where you have a non-trivial homomorphism image of that group. Okay? Whereas some of the ideas that were actually started here, they just gave criteria where you would have a normal subgroup. One of the high points of this theory, is actually Glaubermann's so-called Z-star theorem, which gives a conditions under which a group actually admits a non-trivial normal subgroup. So this is this third main thing that actually happened in the 50s, which actually changed the whole structure of this the way the groups were actually analyzed. If you see the textbooks in group theory until 50s, 60s, I don't know many of you have seen this, the group theory books by Scott and just Marshall Hall and so on, and the later books that came, just they look very, very different. And much of this is just influenced by this. Okay, this is actually about this classical groups. But there is another class of, most of the groups I have described so far, they just fall into some infinite families, like alternating group or GLN or orthogonal groups and so on. But just these are just there are 26 just sporadic groups which don't fall into any particular family. In fact, the term sporadic was used by Burnside when he was just trying to describe this Matthew groups, and that has just stuck. And these 26 groups, they actually appear. Of course, groups are actually symmetries of objects, symmetries of mathematical structures, and these things actually appear as symmetries of very, 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 very special kind of mathematical situations. For example, I have listed a few of them. One of the simplest, the first two things definitely appear in the construction of the monster also. One is the partition of this FQ or N, that is by spheres, by what is called the linear perfect Hamming cone. That is, you look at FQ power N, is the n tuples of elements of FQ. You can actually define a metric of that by just saying that any two n tuples are at a distance t, if at t positions, just this xi is different from yi. That is, distance between x and y is t. If the set of i's at which xi is different from yi is equal to t. And with that, it becomes a metric space, and so you can talk about just spheres, and you can just consider the classical problem of packing this space by these spheres, and that gives to some that leads to some very distinguished packings, and automorphisms of one of those things is actually this sporadic. And there are also various kind of exceptional situations. I have listed a few. For example, exceptional non-split extensions. Okay, appears as centralizers of involutions. And the Lie algebra corresponding to E8, the complex Lie algebra. Okay, that admits a very unique kind of decomposition as a direct sum of so-called Cartan subalgebras, such that the product of any two of these factors in that is so if this Cartan's Lie algebra can be written as direct sum of hi, where just this implies that xy belongs to hk. So decompositions like this was investigated by Thomson. I don't know why, but and one of them leads to this simple So I think many of the the origins of many of these like this sporadic groups is like this rather very special. And one amazing thing I just find is that just this axioms of the group with the additional condition that there exists no normality leads to a very large number of extraordinarily attractive mathematical objects. It actually unites a very large number of extraordinarily attractive mathematical objects. And that is, but that is of course by sheer force of logic. And there is a proof, but why these exist, how these exist mathematical objects of very distinguished properties like this gets united by these things is not very clear. But anyway, people are actually hoping that the number of sporadic groups is infinite and so on because they are so attractive objects, but that was not to be. Even some as important a figure like Richard Brouwer was actually saying that it's not clear whether the number of sporadic groups is infinite or not, is finite or not. Okay. In the sporadic phenomena, there is a, see, I think there is an article by John Thompson. He has written in honor of in a volume produced in honor of Philip Hall, and he recounts some of his earlier experiences and interactions with people like Philip Hall and Wheeland when he was developing his initial ideas, and he makes some comment about why these sporadic groups really occur. A failure of arguments in the presence of the extra special two groups gives rise to the sporadic simple groups. This is a fairly vague statement, but I think there is a great deal of truth in this. Maybe I should recall what an extra special two group is. It's a two group where commutator subgroup is equal to the Fratini subgroup, which is equal to the center of P, and they are all of order 2. This is the analog of this Heisenberg group in Lie theory. And Heisenberg group, just the ubiquity of Heisenberg group is very well known and very well documented. And these extra special two groups also seem to play a very, very central. There is a slightly technical notion called what is known as a group having a extra special two group, a large extra special two group. That essentially means what I have written there. Centralizer, an extra special two group Q of G is said to be large if centralizer in G of Q is the center of Q, which is Z, which is a group of order 2. And this Q is normal in centralizer in G of Z, and Q is not contained in normalizer in G of K for every non-trivial subgroup of order. Last thing is a fairly technical thing, but the main point of this concept is that most of these sporadic groups have large extra special groups. And if a group has a large extra special groups, it would be known it's very close to being simple. Anyway, so in his recent account of the theory of sporadic simple groups, Aschbacher characterizes many sporadic simple groups by the following property. I mean, you see that the presence of this extra special two group is rather very clear. Okay, and in fact, he characterizes many groups with this property. A group satisfying this hypothesis H n L. So n is a positive integer. L is just a finite group, of course, and you are talking about the groups G which satisfies this property. It contains involution so that it's the generalized fitting subgroup of centralizer in G of Z is an extra special two group of order 2 to the power of 1 plus 2n, and centralizer in G of Z over Q, that is the group L you start with, and Z is not weakly closed in Q with respect to G. Okay, which means that there are exist in Q, there are other involutions which are conjugate to Z, and that's what weakly closed means. And the generalized fitting subgroup, this is a concept introduced by Bender, and it is the product of the fitting subgroup and the layer of the group. Layer of the group is like this, this product of semi-simple subgroups which are subnormal. Yeah. Anyway, I have just defined these things, but these are fairly tricky. But anyway, the point is, if a group has a large extra special subgroup contained in that, it is almost simple. And most of the sporadic groups have that problem. Anyway, this is a list of groups, just for example, just this M24 is a group characterized by this property, which means that it has an extra special group of order 2 to the power of 7, and that we have the group L in that case was LP of 2. And this monster is characterized by this. There's an extra special group of order 2 to the power of x24, and this L is this Conway group. Okay. The point here is this. See, in the case of groups of Lie type, the analogs of matrix groups I just defined, I just mentioned, there is a uniform concept called this Bruha decomposition. That is the double coset decomposition of the group, which actually gives a quite a good deal of information about these groups in a uniform way. For example, you would actually know the subgroup structure of subgroups containing the normalizers of Xilo P, for example, which actually gives rise to this concept of building. And but there is generally no uniform concept which actually just unifies these sporadic groups. And I think this statement of Ron Solomon, I think is a still elusive below the wisp is an elegant set of axioms in the spirit of Tits axioms for a building, defining a class of geometries for all finite simple groups, and perhaps more, but not too much more. This is actually something, there is actually the Tits concept of buildings that actually unifies all groups of Lie type, whereas a concept which actually unifies all simple groups and which is not very, which perhaps, his use of the word below the wisp also just seems to indicate whether he says that he perhaps is not very hopeful about that. Okay, this is the classification of statement. So any finite non-abelian, any finite simple group is either a cyclic group, there's an alternating group, or one of the 16 infinite families of groups of Lie type and 26 sporadic simple groups. Some remarks, of course, this looks like a very crisp kind of statement, but you need to define all these groups, and just that itself just takes very, very long. Defining each one of these groups is actually a fairly complicated kind of affair, particularly these sporadic groups. But one central theme that actually emerges is that every simple group contains an involution. Simple again means I mean a non-abelian simple. Every non-abelian simple group contains an involution, and involutions play a very central role in the structure of simple groups. Okay. Remarkably, all non-abelian simple groups except one infinite family contains elements of order 3. Okay. Whether they actually play any major role in the structure of these groups is not very clear. And most simple groups are of Lie type, that is actually one of these infinite families. There is a uniform way, just this, they can be described. But all groups of Lie type, the Coxeter groups, that is the reflection groups, they actually play a very significant role. That is the one which by which the double cosets I mentioned are just the parameterized. Diagonal groups and more generally reflection groups, extra special groups. The extra special groups also, just as I mentioned, they play a very important role in these sporadic things. And the algebra of octonions, they seem to play a very important role. The algebra of the octonions and some structures made by them, they're just very, they're the natural kind of objects. For example, octonions itself, there is just a 27-dimensional exceptional algebra, the so-called Jordan algebra, and the projective plane, coordinatized by octonions. These are the ones which give these groups of type G2, F4, and E6. But most finite groups are nilpotent, as he said, but they use in huge numbers. And the solvable groups, are the ones where the composition factors are all groups of or abelian simple groups. Another perhaps a below the wisp here may be whether one can develop a theory analogous to these solvable groups where the set of composition factors you just choose is not abelian simple groups but a larger class of simple groups. I don't know, it's very interesting to see if there is any even partial work on this. Okay, because of the classification, many of these earlier problems that they were around, they got classified. I mean, they were sorted out. And well, of course, I have not tried to make a complete list. These are all just very old lists, basically. These were almost solved almost immediately after the classification. But one very important thing is that, many questions are reduced to questions about, any questions about finite groups are reduced to questions about simple groups. And in simple groups, you just verify them and just try to solve that problem. And one thing which has not been amenable, which is perhaps of very great interest, is that it's not clear whether which finite groups can appear as the Galois groups of number fields, that is extensions of rational numbers. This has not been amenable to reduction to a problem about simple groups. But that is, if you solve this problem for solve finite simple groups, whether it solves the general question or not is not very clear. Okay, so I'll just very quickly go through this list. This is the finite simple groups of Lie type. All these things are essentially this, matrix groups. AN, BN, CN. Okay, I'll just come to that list. See, this is what Chevalley did. You take an indecomposable root system and a field. He gives an algorithm. He just gives a method to associate a group with the root system and the field. And if you take K to be a finite field, you get these finite groups. Okay. The non-abelian sections of these groups, would be the finite groups. So this is the big revolution which was held by Chevalley in his very famous Prohoku paper. In fact, Walter Fate in one of his places, in one of his articles, he puts in record that this perhaps is the most important paper in algebra, just in the 20th century. So this really has a very important role. And of course, these groups are, just the classical groups, they all just fall into this family. And the exceptional groups, that is G2K, G2Q, these are and the so-called twisted groups. You see, some of these groups admit under certain situations some additional outer automorphisms. See, except in this case of this D4, this is orthogonal group, hyperbolic type. These outer automorphisms are all of order 2, and their fixed points, just would be simple groups. The main point here is that these groups also admit this BN structure, and so they fall into that general theme that Chevalley So all the groups I just mentioned above are actually so-called like this finite groups of Lie type, and except for some small orders, they're all just. But there was actually another very important revolution. This was actually by Steinberg. He actually realized all these groups of Lie type as the fixed points of endomorphisms of linear algebraic groups or an algebraically closed finite field. So I think this actually gives a way of actually relating finite groups of Lie type to actually the theory of algebraic groups, and many of these things can be actually studied more uniform. And as I said earlier, it is the octonions, just are the ones which actually give structures to understand this group G2, Q, F4, and V6 in a natural way. And there is actually this the theory of Tits magic squares. It actually gives a way of constructing these groups of type E7 and E8, which is quite complicated. But the main point here is this: the groups are actually symmetries of mathematical objects. And in all these cases, there are some very natural geometries for which these groups can be realized. For example, like PSLN plus 1 cube is corresponds to this projective space of rank at least 2. That is the partially ordered set of non-trivial subspace of this. And you have just very, very well-defined kind of geometries for all other groups of this type. I would like to particularly draw your attention to this. There is something called inversive plane. This is one of the analogs of these planes, that is rank 2 geometry, which gives rise to these Suzuki groups and something similar for V groups. But anyway, the point is that there is a natural class of geometries, whose automorphisms, the nonabelian sections of their automorphism groups are exactly these groups of Lie. And all these things is facilitated by the existence of P and. And many of these groups, can be, as I said earlier, starting with Dixon, many of these exceptional groups. See, orthogonal groups are the ones which are automorphisms of a vector space which gives a non-degenerate, symmetric, or a quadratic form invariant. Some of these groups like this G2 and this E6, they can be F4. They can be realized as elements of GLV which leave certain multilinear forms invariant, bilinear, trilinear forms. Like G2, for example. In fact, Oshbacher develops his whole theory of G2 and E6 in that setup, and there are some efforts by people like Cooper-Stein and so on, which perhaps is not complete, for the groups like these. Okay, so I think, special features, this is essentially what I've been telling all along. It admits what is known as the BN structure, which in the case of finite things, this B is the normalizer of a silo P subgroup corresponding to that. Okay, and N is the normalizer of this torus group. Anyway, so this see, by using this groups admitting a BN structure, you can construct this geometry for this group whose automorphism group will be this group. And this broad decomposition allows you to just write various things related to this group in terms of this root system and the field. For example, I have indicated the order of this group. You see, this has only information about indexing Coxeter group. Okay, and many other things can be many other structural properties of groups of this Lie type can be described in a uniform way in terms of this root system and so on. And for the sporadic group, we don't have any other property, anything like this. But there is at least one very important feature of these groups of Lie type, what is known as the characteristic of that group. A prime number P is said to be the characteristic of a finite group if it exists, if it has this property for every P local subgroup. And for at least groups of Lie type, just the characteristic is the characteristic of the field on which this group is just defined. And so this actually defines this actually class of these actually parabolic subgroups of G, which are these actually conjugates of the normalizers of actually P subgroups. And with that you can actually construct that geometry. I mean, just the geometry, there is an algorithm essentially described by Tits to actually construct that geometry. The main point of this is this. What Oshbacher and several others have just tried to do is, you look at the normalizers of P subgroups for a sporadic group. You look at the lattice of subgroups which contains the normalizer of a P subgroup, and you can try to see whether you can construct a geometry which is analogous to this Tits building and try to just understand it. And but unfortunately, for even for a group like Monster, there could be more than one natural candidate, which just okay. Well, there are 26 groups. I don't think there is much point in actually going through this list because they're all just names anyway. I can't describe any of them. And the methods of discovery. One is the Matthew group. The earliest one to be discovered, they were discovered as highly transitive permutation groups. In fact, if T is greater than or equal to 4, T is greater than or equal to 4, the only T transitive permutation groups are of course Sn, and the alternating groups are an appropriate N, and these exist Matthew groups. And these things appear as the automorphisms of certain. Okay, maybe I'll just describe one of them. See, for example, this M24. This is the largest of these Matthew groups. This appears as the automorphism group of a 24, 8, 5 code over F2. What does this mean? This means that you look at a vector space of dimension 24 over F2. I'm sorry, this is okay. So that should be the parameters. I'm sorry for this mistake there. So this is a vector space of dimension that is F2 to the power of 24. In F2 to the power of 24, you have a subspace of dimension 12, such that if you look at any vector and the weight of that vector is at least 8. Okay, and but just so this is actually related to the packing problem I just mentioned. This is one way these Matthew groups are obtained, and well, I think I will go. But the second one, this is actually the so-called Conway groups. Okay, we call that a lattice of rank n is a free abelian group of rank n with an integer valued positive definite symmetric bilinear form. Okay, such things were classified. There are 26 distinct such lattices, out of which one of them is very distinguished, and it has these properties. And the important thing is that the property 3, that it has no words whose length square is 2, but it has vectors elements whose length square is 4. This is what is known as the even unimodular lattice without proofs. there is only one such lattice. I have written that explicitly here. But the point is that Conway just calculated just the commutative, it's the automorphism group, and that has just it has a subgroup of order, subgroup of index 2, which is a simple group, and it also just fixed points of several elements of that lattice that also just gives this simple group, the so-called other Conway groups and Matthew group, McLaughlin group and Highman-Sims and so on. Anyway, so this Leech lattice, this gave rise to a few okay, this is the main theme I really wanted to come, centralizers of involutions. Sometime okay, I think you see this centralizers of involutions. I mean, these are a very important aspect of these simple groups. If you look at this, both this as well as the next theme I'm going to talk about is to actually see how these study of these centralizers just lead to some very natural geometric structures that lead to some large families of simple groups. Okay, in the 1940s, Richard Brouwer showed that some very simple properties of involutions leads to very deep insight into the structure of groups, and this property is this is almost a very simple, very trivial exercise, I would say, but I think this is very important. These are very special properties of involutions. If P and U are involutions in any group, then the subgroup H of G generated by them is a diagonal group of order 2n. This doesn't happen if even one of them is not an involution, and if T and U are arbitrary elements, there is no chance anything like this happens. This is something very, very special to involutions. And this is exactly what Brouwer's program exploits. So if n is odd, that is the order of the product is odd, then T and U are conjugate, and if n is even, then Tu contains a unique involution. Okay? And these are all just very easy statements to verify. Well, a very simple consequence of this is the Thomson's order formula, group order formula. It says that if a group G has at least two conjugacy classes of involutions, if U and V as representatives say, then you can write down a formula for the order of the group. You only need information about the centralizer of U, centralizer of V, and the centralizer of G, C, G of Ui, where centralizer of Ui's are this. See, if you take any pair X and Y, their product, just their product belongs to exactly one of those involutions that we have listed here, and this is a very fairly simple counting argument, and this has been very effective in well, I have written the proof, but this is a very elementary counting based. See, for example, the number of elements in UG cross VG that is calculated. But there is a more complicated, this idea can be pushed further, and even when the group has only one conjugacy class of involutions, the order of the group can be written down, but this is a little more easy. And this statement also is very important and very, very seminal, I would say. The Brouwer, if T is an involution of a non-abelian simple group, he in fact at that time wrote non-abelian simple group of odd order. Non-abelian simple group of even order. You remember this is a theorem in 1953. And centralized in G of T has order n, G can be embedded in the alternating group on n square minus 1 symbols. So what this says is that if you just fix the centralizer in G of t, if you fix the centralizer in G of t, the number of simple groups which has an involution whose centralizer has that structure is a finite set. If you fix Cg of t, the number of simple groups with that having a centralizer of an involution of that structure is a finite set. And that's why he just proposed that finite groups can be just classified, just by their. See, in view of this, Brouwer just initiated this program of classifying simple groups. Centralizers of involutions, and along with this, there are just two other very, very major, well, I would say monumental works. One was, of course, Thomson's proving that Frobenius conjecture, which is another way of saying is that a finite group admitting a fixed point, this is not fine, fixed point free automorphism of prime order is nilpotent. There was another very simple figure. And another is this very major work of Fate and Thomson, which shows that any non-abelian finite simple group has involutions. And another very sequence of about 6 papers or so, just totaling to about 450 pages or so by John Thomson, who classified all non-abelian simple groups such that the normalizer of each P subgroup is actually solvable. This is the so-called N group paper. A simpler formulation of the idea of this paper is actually rather quite simple. The fact is that you are looking for actually simple groups. You are looking for the smallest simple group. So one way of actually looking at smallness of the simple group is that the group is not simple, but every subgroup of it is actually solvable. Okay, I mean that's a very particular case of this, and just these two particularly, and this actually introduced so many ideas, which has eventually led to the classification of actually simple groups. And well, this is the Thomson's N group theorem. Well, I mean, just the groups with the property that normalizers of any solvable subgroup or greater than 1 is solvable, then G should be one of actually these things. And this had lots of consequences, and one of them is just a consequence like this. This is just a characterization of solvable groups. A group, I'll just point out one thing. G is solvable if and only if X, Y, Z are 3 non-identity elements of G of pairwise co-prime orders. Then X, Y, Z is different from 1. Every pair of elements of G generates a solvable subgroup. This is equal to G is solvable. And there are just many consequences of this type, but the most important significant part of this theory is that it introduces a lot of techniques, which just like to. No, this Brouwer's program was very successful. Many sporadic simple groups were just discovered by this way. And a typical kind of theorem is this. This is one of the earliest theorems of Brouwer. Let G be a finite group satisfying this property. There exists an involution such like this. So you are actually starting with an involution of a known type, and there is an additional technical conditions. Then the group G should be necessarily one of known type, and there are some exceptions. So it is this exceptional kind of things which actually has generated most of these well, this is just a list of. Well, I think I should actually mention this. The important, see this Walter Feit commenting on this insight was commenting that this insight was far from obvious. Walter Feit mentions that this eluded even a mathematician of the caliber of Burnside, particularly after he had proved the following beautiful theorem. SL2 to power A are the only simple groups of even order in which the order of each element is either 2 or odd. So he had actually proved a theorem which actually signifies the importance of elements of order 2, but anyway, just if you just fix the centralizer of involution, there could be other groups other than just the one you actually get started with. This is what Suzuki calls the satellites. The next theme, okay, the next theme perhaps I will talk about in the next lecture. But the next theme was another avalanche of ideas. Another avalanche of ideas started by Fisher. And there are several other things, I should mention. I'm just pointing out only these two main things. And the idea here is this. See, all of us know that Sn is just generated by a conjugacy class of involutions, that is transpositions, so that the product of any two transpositions is either 1, 2 or 3. Okay, he wanted to he started thinking about classifying groups with the property that it is generated by a conjugacy class of involutions. Again, please remember involutions. Conjugacy class of involutions such that there is a restriction on the product. There is a restriction on the product of, there is a restriction on the orders of the product of any pair of elements of that conjugacy class. In transposition, the product of any two elements in any two transpositions is either 1, 2 or 3. Okay? He started classifying groups like this. I just say the conjugacy class D of involutions is said to be a class of P transpositions. The product of xy is 1, 2, P for all xy belong to X. And the group G is said to be a P transposition group. He started trying to understand things like this, and this led to lots of geometric ideas and many simple groups, so-called Fisher groups and so on. But I think what is very important is that this very algebraic kind of this condition, the geometric ideas follow very, very naturally. Because just this many matrix groups have generators, the so-called transfections, which will have very similar kind of properties. I think I'll stop here, but